Welcome to the Deep Dive, the show where we take really complex, sometimes mind-bending topics, and we'll try to distill them into something fascinating and easy to grasp just for you. Today, we're tackling something you experience every single second. It's completely fundamental, but, you probably take it totally for granted. We're talking about time. We all live by the clock, right? Setting appointments, measuring our life, feeling that constant push forward. But what if I told you that our gut feeling about time, it's fundamentally wrong according to modern physics. What if time just isn't what you think it is? Okay, let's unpack this. This deep dive is going to be a bit of a journey. Think of it like a high-speed tour through physics, relativity, quantum mechanics, cosmology, all showing how our everyday idea of the clock has been, dismantled. We've got a great stack of sources for this, a mix of cutting-edge science and these really groundbreaking ideas that challenge, our basic assumptions about reality itself. Our mission today, give you a shortcut, a way to get genuinely well-informed about one of the biggest mysteries out there. And trust me, there are going to be some serious aha moments.
Absolutely. And what's fascinating here is just how deep our standard idea of time runs, and how truly revolutionary this shift in physics has been, mostly in the last century or so. We're not talking small tweaks here. It's a total rethink. It affects everything, how we think about memory, causality, even the whole structure of the universe. So yeah, prepare to have your mind stretched a bit.
Okay, so let's start at the beginning with what we could call the old clock. For centuries, the main view of time, the one that still feels right to most of us, that steady tick-tock forward march, came from Isaac Newton. Newton saw time as this absolute background, something that just flowed uniformly, independently, didn't matter what else is happening in the
Right,
universe.
like a giant invisible metronome for everything.
Exactly. Ticking away perfectly, the same everywhere, completely unaffected by stars or planets or us. It was the cosmic constant.
A single universal rhythm.
Yeah, everyone, everywhere shared the exact same timeline. Your clock, my clock, a clock light years away, theoretically, they'd all tick in perfect sync.
And this idea became the bedrock of classical physics, didn't it?
Totally. It let scientists predict things with incredible accuracy. Falling apples, planet orbits.
It really worked for that era.
And it fit perfectly with the mechanical age, too. Pendulums, gears. They all seem to reinforce this idea of perfect, regular ticking.
It felt very intuitive, like the unchanging stage for everything that happens.
It was the absolute backdrop.
And, that absolute view wasn't just powerful scientifically, it was also, well, comforting, philosophically speaking. It gave us this stable, linear path, past, present, future, a clear timeline everyone could agree on.
A universal now.
Exactly.
Yeah.
A moment that was simultaneous for everyone, no matter where they were or how fast they were moving. For centuries, that was just fact, unquestioned. It underpinned classical mechanics, predicted planetary motion incredibly well, kind of paved the way for the Industrial Revolution, that whole mechanistic view of the world.
Shaped our language, even.
Yeah, our metaphors, our sense of how things unfold, it really felt like the solid foundation of reality.
But then, along comes Albert Einstein. Young guy, working in a patent office. And here's where it gets really interesting. 1905. His theory of special relativity, boom, it just shattered Newton's absolute time.
Completely turned it on its head.
That giant universal metronome, suddenly it looked like, just an illusion, or maybe a local approximation at best.
So what's the core idea then?
The core idea is genuinely mind-blowing. Time isn't absolute, it's relative.
Relative, meaning?
Meaning your experience of time, how fast it actually flows for you, it changes depending on your speed, how fast you're moving.
And this isn't just theoretical.
Not at all. It's a real measurable thing. Physicists call it time dilation, put simply. If you move really, really fast, like close to the speed of light.
The ultimate speed limit.
Right. Time for you literally slows down compared to someone who's, say, standing still or moving much slower.
Why does that happen? What's the underlying reason?
It comes down to one of Einstein's key postulates. The speed of light in a vacuum is constant, always the same speed for everyone, no matter how fast they're moving or how fast the source of the light is moving.
Okay, that seems simple enough, but...
But the consequences are huge. If light speed must be constant for everyone, then something else has to give when observers are moving differently relative to each other.
And that something else is?
Our common sense notions of space and time, they have to stretch and contract to keep light speed constant for everyone.
So space and time become flexible.
Exactly. Think about it. If you were a photon traveling at light speed, time for you would completely stop. And distances in your direction of travel would shrink to zero. It's bizarre.
Okay, that's wild.
Yeah.
What about that twin paradox example?
Ah, yes, a twin paradox. It's the classic illustration. Imagine identical twins. One stays on Earth.
Okay.
The other twin gets in a super fast spaceship, zooms off near light speed, travels around for what feels like maybe a few years to them.
Right.
When that traveling twin comes back to Earth, they'll find they've aged way less than the twin who stayed home. Years less, potentially.
And this isn't just a thought experiment.
Nope, not science fiction. It's a genuine prediction from the physics, a direct result of time dilation. The real aha here is that time isn't just a passive background. It's tied up with your motion. Your speed literally changes your experience of time.
So we have actual proof.
Oh yeah, loads.
Yeah.
Real-world evidence confirms it over and over. Take muons.
Muons. Tiny particles.
Yeah, tiny unstable subatomic particles. They get created way up in the atmosphere when cosmic rays hit it. They have super short lifespans. They should decay almost instantly.
Meaning they shouldn't reach the ground?
Exactly. They shouldn't have enough time. And here's the thing. They're created moving incredibly fast, often near light speed.
Ah, so time dilation kicks in.
Right. From our perspective down here, their internal clocks tick slower. It stretches their lifespan just enough for many of them to reach the Earth's surface, way further than they should be able to travel.
That's compelling evidence.
And it's not just particles. We've done it with super precise atomic clocks. Fly one around the world on a jet, compare it to one that stayed put.
And they show a difference.
A tiny, tiny difference, but measurable. And it matches Einstein's predictions perfectly. It feels weird, counterintuitive, but it's a proven fact about how our universe works.
And it's really important to stress this isn't just like an illusion or some trick of how we see things.
Right, it's fundamental.
It's a genuine property of reality itself, of this interwoven fabric physicists started calling spacetime. Because you can't really separate space and time anymore after Einstein. They're linked.
Space-time, one thing.
Yeah, time isn't just happening to you. It's woven into your movement through this four-dimensional fabric. And the really deep implication here, there's no single universal now.
No universal present moment.
Nope. Think about two events happening far apart, say, on different planets. If you have two observers moving differently, they might not agree on whether those events happened at the same time. Simultaneity itself becomes relative.
Wow, so my now isn't necessarily your now if we're far apart and moving differently.
That's the essence of it. It all stems back to that constant speed of light.
Yeah.
It forced this complete rethink, merging space and time into space-time. And when you see it like that, time stretching and compressing, it starts to make a kind of strange sense, doesn't it?
It does. Like our everyday feeling of time is just our local slice of it.
Exactly. A particular perspective within the larger reality of space-time, but definitely not the whole story.
Okay, so time is personal. It depends on your speed. That's already pretty wild. But Einstein, he wasn't finished.
No, he kept going.
A decade later, 1915, he drops general relativity on the world. And this takes the whole flexibility of time thing even further.
How so? What changes?
Now, it's not just motion affecting time. Gravity gets involved too.
Gravity affects time. Seriously.
Seriously. The core idea of general relativity is that massive things, planets, stars, black holes, even us, though the effect is tiny for us, they don't just pull things with an invisible force. Instead, they actually bend and warp the fabric of space-time around them, like putting a bowling ball on a stretched rubber sheet. It creates a curve.
Right. I've seen that analogy. Gravity is geometry.
Exactly. And here's the kicker. This bending, this curvature of space-time, it slows down time.
Whoa. Okay. Slows it down how?
It's called gravitational time dilation. Basically, the stronger the gravity, meaning the closer you are to a massive object, the more space-time is curved, the slower time ticks.
And further away.
Further away, where gravity is weaker and space-time is flatter, clocks tick faster. Maybe only infinitesimally faster, but faster nonetheless.
That's incredible. Gravity literally bending time.
Yeah.
Can you maybe explain why gravity does that a bit more? And is there a really clear everyday example? Because it still sounds pretty abstract.
Sure. Think about light again. Light always wants to take the shortest path through space-time. But near a massive object, space-time itself is curved.
Like the rubber sheet analogy.
Yeah.
Exactly. So light has to follow that curve. And for light speed to remain constant for all observers, time itself has to slow down in that curved region from the perspective of someone outside it. Okay. So the curvature forces time to adjust. Precisely. Imagine a clock way down deep in a gravity well, like near a black hole, versus one far out in space. The clock near the black hole would seem to tick incredibly slowly compared to the distant one.
And for someone near the black hole.
For them, looking out, the rest of the universe would appear to be running in fast forward. It's a real effect. And like you asked, it's not just theoretical, it's part of our daily tech.
Daily tech? How?
Okay, the perfect example, GPS satellites.
Our phone navigation.
Yep. Those satellites are orbiting way up high, about 20,000 kilometers up. Earth's gravity is weaker up there than it is down here on the surface.
Right. Less gravity means?
Means time runs slightly faster for the satellites compared to us on the ground due to gravitational time dilation. They gain about 35 microseconds every day just from that effect.
Okay, faster because of weaker gravity.
But wait, there's more. They're also moving really fast, about 14,000 kilometers an hour.
Ah, so special relativity kicks in too. Motion slowing time down.
Exactly. Because of their speed, their clocks tick slower relative to Earth clocks by about 7 microseconds per day.
So one effect speeds time up, the other slows it down.
Right. You combine the two, the gravitational effect faster and the velocity effect slower. And the net result is that the GPS satellite clocks actually run faster than ground clocks by about 38 microseconds each day.
38 millionths of a second. That sounds tiny. Does it really matter?
Oh, absolutely. If the GPS system didn't constantly correct for both these relativistic effects, which it does, automatically the positioning errors would build up incredibly fast. We're talking kilometers of error within hours. Your phone would be useless for navigation.
Wow. So this mind-bending physics is actually running inside my phone right now.
Pretty much. It's a fantastic, concrete example of relativity in action.
It really makes you think how fluid time is.
It does. And this isn't just for huge distances or speeds. Even climbing a mountain makes your clock tick infinitesimally faster than someone at sea level because you're slightly further from Earth's center and slightly weaker gravity.
So it's happening everywhere all the time.
All the time. It's been measured with atomic clocks. It just hammers home how deeply gravity and time are linked. General relativity really changed the game. Space-time isn't just a passive stage anymore.
It's an active player.
Exactly. A dynamic thing, bent by mass and energy, and that bending dictates how things, including time, behave. If we connect this to the bigger picture, it tells us time is woven into the universe's geometry. It's a dimension that literally stretches and bends.
Okay, so we've gone from Newton's metronome to Einstein's flexible, stretchy, gravity-bending river of time. Mind blown. But now, let's shift gears again. Let's dive into the really weird world of the very small, the quantum realm.
Ah, quantum mechanics. Things get strange here.
They really do. And here's where it gets super perplexing for time. Because quantum mechanics, the theory that describes atoms and particles incredibly well, it treats time very, very differently from relativity.
How so?
Well, in most standard quantum theories, time kind of snaps back to being like Newton's clock. It's treated as this absolute external parameter again, a fixed background.
So, not relative, not flexible.
Nope. Think about the most famous equation in quantum mechanics, the Schrödinger equation. It describes how a quantum system, like an electron's wave function, evolves. And it relies on t-time being this fixed, linear, absolute thing that just ticks forward universally.
Like an external clock controlling the quantum changes.
Exactly. Time isn't part of the quantum system itself. It's the timer outside the system that everything happens within.
Which is completely at odds with relativity.
Completely. It creates this massive fundamental mismatch right at the heart of physics. Relativity, time is dynamic, flexible, part of space-time. Quantum mechanics, time is fixed, absolute, external.
A major contradiction.
Yeah. So what does this mean practically? What happens when physicists try to, make these two giant theories talk to each other? This problem of time, as you called it.
Right. The problem of time. It becomes a huge roadblock when physicists try to create a unified theory, what they call a theory of quantum gravity.
Quantum gravity, the theory of everything.
Essentially, yeah. A single framework that handles both the really big stuff, gravity, cosmology, black holes, described by general relativity, and the really small stuff, particles, quantum phenomena, described by quantum mechanics.
And the different views of time get in the way.
Massively. How do you merge a theory where time is dynamic and bends with gravity with a theory where time is this rigid, external background parameter?
Sounds impossible.
It's incredibly challenging. How can time be fundamentally relative and flexible and simultaneously an absolute fixed backdrop? It's like trying to combine oil and water at the most fundamental level of reality.
And there's no sort of time operator in quantum mechanics either, right? Like there is for position or momentum.
That's another fascinating point. In standard quantum mechanics, unlike position or momentum, there isn't really a straightforward time operator that works in the same way. This hints again that time might have a different, perhaps less fundamental status compared to space.
So this whole mess, it really makes you wonder, doesn't it?
It absolutely does. This raises an important question. Could our basic understanding of time just be incomplete? Maybe the way we experience it, and even the way our best theories are currently set up, is missing something deeper about what time actually is.
Could time itself be not real at the deepest level?
That's exactly where some of the most mind-bending physics is heading.
Okay, so this conflict between relativity and quantum mechanics, it leads us to perhaps the most radical idea we'll discuss today. What actually happens when physicists do try to write down equations that combine quantum mechanics and general relativity?
Well, the results are often strange, to say the least.
Strange.
In many of the serious attempts to formulate a theory of quantum gravity, something really weird happens. Time just seems to vanish from the fundamental equations.
Vanish, like it's just not there.
Pretty much.
Yeah.
Take one famous example, the Wheeler-DeWitt equation. It's an attempt to describe the quantum state of the entire universe. But when you look at the equation, there's no t, no time variable doing the evolving.
So what does it describe then?
It seemed to describe a static, frozen universe, like a single, timeless snapshot. No past, no future, just an eternally existing block. And this isn't just some weird math trick.
Apparently not. It pops up in various approaches, some interpretations of string theory, loop quantum gravity. It's a recurring theme that strongly suggests that maybe, just maybe, time isn't fundamental at all. It's not part of the basic building blocks of reality.
Wow, okay.
Yeah.
That's hard to get your head around. A timeless universe.
Right. It's one of the deepest puzzles going. So if time isn't fundamental, what could it possibly be? How do we experience change and flow?
This leads to this really fascinating alternative.
Yeah.
Maybe time is emergent.
Emergent, like it arises from something else.
Exactly. Think about temperature. Is temperature a fundamental property of a single water molecule?
No, I guess not. It's about how lots of them are moving, right?
Precisely. Temperature isn't fundamental to one atom. It emerges from the collective behavior, the average kinetic energy, of countless atoms jiggling around. You need the crowd for the property to appear.
Okay, I get the analogy. So time could be like that.
That's the idea. Time might not be built into the bedrock of reality. Instead, it could arise from something more fundamental, maybe from change itself, from the relationships and interactions between different parts of the universe.
So it's a byproduct, not the stage.
Sort of. It's not the pre-existing river we're all flowing down. It's more like the patterns made by the flowing water, if that makes sense. In this view, time might only really exist from the inside when observers like us perceive differences, measure changes, and experience events unfolding.
It's a perspective, not an absolute.
Exactly. The ultimate aha here is that time, as we know and feel it, might be a feature of the universe's activity and our interaction with it, not a fundamental dimension it exists within. This connects to ideas like the block universe.
The block universe, where everything just exists.
Yeah, the idea that all of space-time, past, present, future, exists as one static four-dimensional block. Our feeling of a flowing now is just our consciousness moving through this already existing block. Time doesn't flow, we just experience it sequentially.
Okay, my brain hurts a little now.
Huh. It's meant to. And the philosophical implications are huge, aren't they? If time isn't fundamental, what happens to cause and effect?
Yeah, if A causes B, but there's no fundamental before and after.
Right. What about memory? What about free will? If the future already exists in this block, it challenges everything we assume about existence.
Okay, so this idea of emergent time, maybe even a timeless universe at the bottom level.
It's wild.
But is it just, theory and equations, or are there any actual experimental clues? Any hints from the real world? Let's break this down.
Well, direct proof is incredibly hard, obviously. We can't exactly step outside the universe to see if time stops. But there are experiments that explore related ideas, particularly the idea that time is relational.
Relational, meaning it depends on relationships between things.
Yes, including the relationship between a system and an observer. Imagine a simplified lab setup. You have two quantum systems. Let's say one acts as a basic clock. Maybe its quantum state changes predictably, like flipping back and forth.
Oh, a quantum clock.
And the other quantum system evolves. Its state changes based on the ticking of that quantum clock. They're interacting.
Got it. Clock and evolving system.
Now, here's the key part. Imagine an internal observer. Someone or something inside this combined system interacting with both parts, seeing the clock tick and seeing the other system change accordingly.
What would they experience?
To them, time would appear to flow normally. They'd see a clear sequence of events. Clock ticks, system changes. Clock ticks again, system changes more. A before and an after, just like our everyday experience.
Okay, makes sense. But what about someone outside?
Now imagine an external observer, someone looking at the entire setup clock plus evolving system as one single isolated quantum entity.
From the outside looking in.
Right. If that whole system is treated quantum mechanically, especially if it's in what's called a superposition of energy states, then from the outside, there might be no apparent time evolution at all.
No time passing.
The external observer might just see a static, unchanging quantum state, a state where the clock and the system are linked, entangled, but nothing is happening sequentially. The whole thing looks frozen, just like the Wheeler-DeWitt equation suggests for the universe.
Is this just theoretical, or has someone actually done this?
Well, there was a fascinating experiment back in 2013 in Italy that provided some really intriguing preliminary evidence along these lines.
Tell me more.
Researchers used entangled photons, particles of light. They essentially set up one part of the entangled system to act as a clock by manipulating its polarization state, and the other part as the evolving system. Then, crucially, they looked at the evolving system from two viewpoints. First, internally, by correlating its state with the clock state. Second, externally, by looking at the quantum state of the whole combined entangled system.
And what did they find?
Exactly what we just discussed. The internal view, correlating the parts, showed a temporal evolution, things changing over time relative to the clock. But the external view, looking at the total state, it appeared static, unchanging. Time seemed to disappear from that global perspective.
Wow. So time depended on whether you were inside or outside the system.
That's what the experiment suggested. The crucial insight here, connecting back to the emergent idea, is that maybe our experience of time flowing is intrinsically linked to us being part of the universe, interacting within it.
Not looking at it from some impossible outside view.
Exactly. If you could somehow see the whole universe's quantum state from outside, maybe it would look static and timeless.
That has really profound implications, doesn't it? It suggests time might not be universal in the way we assume.
It really does. Maybe time only exists, or is only meaningful, from within systems where change and observation are happening. It ties the existence of time to interaction and perspective.
It blurs the line between the observer and the phenomenon itself.
Which is, of course, a recurring theme in quantum mechanics anyway. It's a radical shift, moving away from time as an absolute backdrop to time as something perhaps generated by the very act of observing change within the universe.
Okay, so we've got time being relative, maybe emergent, maybe only existing inside. But there's another huge puzzle about time. Why does it only go one way?
The arrow of time. Yeah, why past to future, never the other way around?
Exactly. Which brings us to another really cool idea about where time, or at least its direction, comes from. The thermal time hypothesis.
This connects time's flow to entropy.
Entropy, right. That's usually explained as disorder, things getting messier.
That's the common way to put it, yeah. The universe's tendency to move from ordered states to more disordered, more probable states. Think of smashing an egg. It goes from ordered whole to disordered.
And it never spontaneously unsplatters itself.
Exactly. Or think of perfume escaping a bottle. It spreads out into the room, more disordered. It doesn't gather itself back into the bottle. That's entropy increasing, the second law of thermodynamics in action. It's about systems tending towards states with more possible arrangements, more microscopic ways to be.
Okay, so things tend towards messiness. How does that relate to time's arrow?
Well, in the thermal time hypothesis, the perceived flow of time, its directionality, isn't necessarily fundamental in itself. Instead, it arises from this constant, irreversible increase of entropy in the universe, or at least in systems like ours.
So time flows because entropy increases.
Sort of. Wherever you see entropy increasing, you inherently have a direction. You have a state that came before, lower entropy, more ordered, and a state that comes after, higher entropy, more disordered. That statistical directionality is what we perceive as the flow of time, according to this idea.
We can't go backwards in time because entropy doesn't spontaneously decrease overall.
Precisely. In any closed system, entropy tends to increase, or at best stay the same in some ideal reversible process. It doesn't go down. So time flows in the direction of increasing disorder. Our very sense of before and after gets tied to this fundamental asymmetry in thermodynamics.
So it's not a ticking clock, it's the universe getting messier that defines time's flow. That's quite a different picture. And does this connect to memory? Like why we remember the past, not the future?
Absolutely. This entropy connection gives a really compelling physical basis for why time has a direction, unlike space where we can move back and forth. And yes, it helps explain memory. Our memories are essentially records, traces left behind of past lower entropy states.
Hmm.
Creating a memory itself involves physical processes that increase entropy overall. The causal chain events happening, creating records, always aligns with this direction of increasing entropy.
You break the glass, you don't unbreak it.
Right. All the macroscopic processes we experience are fundamentally irreversible because of this statistical tendency towards disorder. You can't unscramble an egg. So if we connect this to the bigger picture, the arrow of time, that relentless forward march we feel, might not be baked into the fundamental laws of physics at the micro level, where some laws are time reversible.
It's more of a statistical, large-scale thing.
Exactly. It could be an emergent feature of thermodynamics, a consequence of dealing with systems containing vast numbers of particles whose collective behavior overwhelmingly favors moving towards equilibrium, towards greater disorder.
Yeah.
It's a macroscopic phenomenon.
Born from the statistics of a universe that started in a very ordered, low-entropy state near the Big Bang and has been unwinding ever since.
That's the prevailing cosmological view, yes. This perspective shifts time's arrow from being some fundamental law to being a consequence of the universe's overall state and evolution. Of course, the precise link between this thermodynamic arrow and our subjective feeling of time passing, that's still a really deep mystery.
Okay, wow, what a trip. We started with Newton's simple, steady clock. Einstein smashed it, time became relative, personal, bendy with speed and gravity.
Then quantum mechanics threw a wrench in the works, treating it as fixed again.
Right, leading to that deep contradiction, the problem of time. And then these really wild ideas. Time might not even be fundamental. It could be emergent.
Arising from interactions, from relationships within the universe.
And it's one-way flow linked to entropy, to the universe getting statistically messier.
It's a completely different picture from where we started.
So let's try and bring all this together. How should we think about time now, based on all this? How do we reframe it?
Well, some modern approaches, like certain interpretations of relational quantum mechanics, really push these ideas to their limit. They argue that everything about reality, including space and time, might be purely defined by relationships.
Not just relative to speed or gravity, but relative to everything. Observation, interaction.
Exactly. Your properties, my properties, the properties of a particle, they only become definite in relation to something else through interaction. And time itself might be part of this relational network. It's not just about reference frames anymore. It's about the information exchanged between systems.
So my now is defined by my specific interactions right now.
In this view, yes. It truly destroys any lingering idea of a universal absolute time or now.
Yeah.
The very concept might only make sense locally, relationally.
And what about that idea of time not being smooth? Discrete time.
That's another fascinating possibility coming out of some quantum gravity research, particularly loop quantum gravity. It suggests that space-time itself might not be a continuous fabric. It might be granular, pixelated, made of tiny, indivisible units.
Like atoms of space.
And maybe atoms of duration, fundamental, indivisible chunks of time. A sort of minimum time interval, often called the Planck time, below which the concept of time just breaks down.
Like a cosmic frame rate.
You can think of it that way. If time proceeds in tiny, discrete jumps instead of flowing smoothly, well, that challenges our intuition even further, doesn't it? What does continuous motion even mean then?
So putting it all together, what is time then? If it's not a clock, not just a dimension.
It starts to look less like a fundamental thing and more like maybe a scaffolding of relationships.
A scaffolding.
Yeah, something constructed or emerging from the connections between things, woven from particle interactions, from the physical basis of memory that distinguishes past from future, from the statistical march of entropy, and maybe even from our own perception as observers embedded within the system.
So time emerges from complexity, from the structure of change itself.
That's the direction these radical ideas point. Time isn't the stage. It might be part of the play, emerging from the actions and interactions happening on it.
Wow.
And what's fascinating here is just seeing that evolution and understanding, isn't it? From
Yeah.
Newton's simple clock to this complex, dynamic, observer-dependent, potentially emergent thing.
It's gone from being a simple measurement to, well, part of the deepest fabric of reality.
Exactly. Tied to geometry, quantum weirdness, statistics. It really forces us to reconsider not just what time is, but how we exist within it, how we perceive reality.
It's a powerful reminder, isn't it, that the universe is way stranger, way more amazing than our everyday intuition lets on.
Absolutely. Constantly revealing deeper layers to things we thought were simple. Hashtag outro.
Well, that was quite a deep dive. We've really journeyed from the familiar Newton's absolute time through Einstein's revolutionary relative time and landed in some truly mind-bending territory. Emergent time, relational time, time tied to entropy and observation. I think it's safe to say our gut feeling about time, that steady, constant flow, it's fundamentally different from the picture modern physics is painting.
It certainly is a much richer, stranger picture.
And it's crucial to remember our understanding is still evolving. This is very much an active area of research, isn't it? One of the biggest ongoing mysteries.
Definitely. It's right at the frontier where our best theories, relativity and quantum mechanics, still don't quite mesh. Pushing past that is driving a lot of theoretical physics.
Well, thank you for taking this journey with us today, for daring to question something as basic as the clock ticking. We hope it gave you some things to think about.
Maybe one final thought to leave you pondering. This raises an important question. If time really is emergent, if it maybe only exists or is only meaningful, from within systems where there are observers and interactions and change,
Yeah.
what does that imply about the very early universe, before complex structures or observers existed? Or about vast empty regions of space, maybe even other universes if they exist? If there's nothing interacting, nothing observing, no entropy significantly increasing, does time even flow there? Does it even exist in the absence of consciousness or interaction?
Wow. Does time need us or something like us to even be real?
It's a profound question to mull over. Does time need things to happen within it to exist? Something to think about until next time.